Hello everyone. Today we're going to take a look at section 3.3 where we take a closer look at the unit circle and the significant role that it plays with respect to trigonometric functions. So let's just start by taking a look at a unit circle, which, as you know, is just the circle of radius 1 centered at the origin 0 0. Now, what makes this circle very special is the fact that if we take a look at a central angle measuring theta radians, then if we call the point of interception of the terminal side of that angle with the unit circle the point designated by the ordered pair xy, then we find that when we draw the natural right triangle that is associated with that the length of one leg will be x. As long as we're in the first quadrant, then it's positive. Otherwise, we adjust the sign for x and y. And in the first quadrant, at least, the other leg will have length y. And because the hypotenuse is just another radius of this unit circle, it's going to have length 1, which makes something quite interesting happen. Notice that in this setup, if we look at the sine of the angle theta, remember we use the mnemonic so ka toa. So the sine is opposite over hypotenuse, the cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. So using that, we realize that the sine of theta is going to be opposite, which is y, over hypotenuse, which is 1. In other words, the y value of that point is the sine of the angle itself. So we just get y. Now, if you look at the cosine of theta in this picture, you notice that the cosine is the side adjacent to theta, which is x, over the hypotenuse, which once again is 1. So we end up with x for the cosine. Now, if we look at the tangent of theta, tangent is opposite over adjacent. So we get y over x. Now, if we look at the reciprocals of these functions, we get cosecant of theta. It's going to be the reciprocal of the sine function, so it's just going to be 1 over y. And then when we look at the secant of theta, we get the reciprocal of the cosine function, which is 1 over x. And cotangent of theta is going to be the reciprocal of the tangent function, so it's going to be x over y. Now, when defined in this manner using the unit circle, the trigonometric functions get the name circular functions. So, for obvious reasons. So, the amazing thing is that no matter what angle you look at on the unit circle, then the coordinates of the point of interception of the terminal side with the unit circle will be precisely the sine and cosine. The x value will be the cosine of the angle, and the y value will be the sine of the angle. So this is going to make finding sine and cosine quite simple with respect to some of at least the angles that we're familiar with, such as the 30, which is the same 30-degree angle, which is pi over 6, 45, which is pi over 4, or 60, which is pi over 3. Now, we'll get into that in a minute. However, notice that as far as the sine and cosine functions are concerned, the values are just x and y values on this circle. So there's no angle for which sine or cosine would become undefined. So notice that the domain for sine and cosine is going to be all real numbers. So the formal way of writing that is d, we write the script d and we say that's just equal to r. Or we can write it as an interval, so we can say negative infinity to infinity. Now, the domain for all the other 4 functions is going to be restricted, because if you notice, there are going to be locations for which either the x is 0, that's going to make secant and tangent undefined, and there are also going to be locations where the y is 0, and that's going to make cosecant and cotangent undefined because you get 0 in the denominator. So let's take a look at the locations where the x is 0 first. You know that x is 0 at pi over 2, for instance, and 3 pi over 2. Or you can look at it as at 90 degrees and 270 degrees. So the domain for those functions will be restricted based on that. So for secant and tangent functions, the domain is going to get restricted. So notice that this is 1 pi over 2, this is 3 pi over 2, you can go around, that'll be 5 pi over 2, and then 7 pi over 2. So, or you can go this way and you get negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. So basically we don't want any odd multiples of pi over 2. So we restrict the domain for these 2 functions in this way. We say the domain is all theta such that theta does not equal to 2n plus 1 times pi over 2. This is how we create odd multiples. Notice that let's go ahead and be completely precise and say n belonging to the set of integers. Now, sometimes this automatic shape situation makes this a little bit difficult actually. So notice, for example, if you plug in n equals 0, you get 2 times 0 plus 1, that gives you 1. If you plug in n equals 1, you get 2 times 1 plus 1, which gives you 3. Or you can plug in negatives. Negative 1 for n will make this negative 2 plus 1, which is negative 1. So play with that a little bit and you'll realize that this expression, quantity 2n plus 1 times pi over 2, will give you all the odd multiples of pi over 2. And we're going to go ahead and take those out of the domain for secant and tangent. Now, for cosecant and cotangent functions, notice that cosecant and cotangent get in trouble when y is 0. And notice that as far as ordered pairs on the unit circle are concerned, the locations where y is 0 is one right here, for example, at 0, and one on this side at pi, or you can go around again, so at 2 pi, or go again this way, 3 pi, 4 pi, 5 pi. In other words, we need to exclude all multiples of pi, integral multiples of pi, not just the odd ones or even ones or anything like that. So for these two, the domain, meaning the values of theta that are okay to use, are any value of theta as long as theta does not equal to n pi for all n belonging to the set of integers. So this way we are removing all multiples of pi. And for example, if n equals 0, you get 0 times pi, which is the 0-degree angle or 0 radian angle. If we have n equals 1, we get pi radians. If n is 2, we get 2 pi radians, or you can use negatives. Negative 1 times pi will exclude negative pi, negative 2 times pi will exclude negative 2 pi, etc. So that is the domain and range for all these 6 trigonometric functions. Take a look at what we've just discussed and make sure to pause, fully understand this before you come back to proceed. Okay, so I hope you took the time to absorb all that before you pushed play again. Now, let's take a look at the unit circle again, and we can quickly establish a fact that we already established beforehand, but the unit circle makes it particularly easy to establish that fact. And that is that if you notice and look at this right triangle, one side, one leg, the right angle is right there, one leg is x, the other leg is y, and the hypotenuse again is a radius of the unit circle, so it has length 1. So using the Pythagorean theorem, we get y squared plus x squared equals 1 squared. Now, we could have written x squared plus y squared equals 1 squared as well, but for reasons that you'll see in a minute, we prefer to write the y squared first. So basically that's just y squared plus x squared equals 1. But remember, when you're on the unit circle, the y coordinate is precisely the sine of the central angle associated with it. So that's sine of theta squared plus, and x is precisely the cosine of the central angle, which we just discussed. And remember, this only happens if you're on the unit circle. Otherwise, you won't have, you'll have another identity, but you won't have one on this side. So pay attention to that. Now also notice that the way that we write this without parentheses, you have to put the squared right above the sine, not above the theta, because if you put it above the theta here, it's going to be interpreted as you meaning that you're going to take an angle, square it, and then take the sine. But if you want to make sure people understand that you want to find the sine of an angle and then square the whole thing, you put the 2 right there. Plus, same here with cosine squared of theta equals 1. And this is one of the most fundamental identities in all of trigonometry. It's called the Pythagorean identity. We've already used this previously quite extensively to, for example, find the values of pretty much all 6 trigonometric functions, as long as we know the value of one and the quadrant in which the angle has a terminal side in. But and we will come back to it later, but it was just interesting to show you just how quickly you can establish this identity when you're on the unit circle. We did it previously where instead of 1 we had a general r, and we were still managed to prove that this identity holds. But if you look back in your notes, you'll see that that required a lot more algebra to establish. All right, so the other issue that is very interesting about the unit circle is the symmetry of the unit circle. Now, as far as a object being centered around a geometric object being centered around the unit circle is concerned, it doesn't get any better than a circle, because it's going to have all the different types of symmetry that we are interested in. For example, it is symmetric with respect to the y-axis, this circle. It's also symmetric with respect to the x-axis, and one other important kind of symmetry is with respect to the origin. Okay, so notice that we have 3 types of symmetry going on. So what does that mean for us? It means, let's say you have a point A, B on the unit circle, and of course this holds for other circles as well, but remember, from this point forward we're going to be interested in and working with the unit circle just because it makes things so easy, that hypotenuse being 1. So let's say you have a point AB on the unit circle. What all these different kinds of symmetry, so in other words, with respect to the x-axis, with respect to the y-axis, and with respect to the origin or the point 0, 0, what this indicates is that if the point AB is on the unit circle, then symmetry with respect to y-axis tells us that this point here is going to be on the unit circle as well. So go ahead and pause and guess what that point is before you play again. Okay, so you should have realized that if that's AB, that should just be the point negative AB. All right, I should draw it a little bit probably further up right here. And the symmetry with respect to the x-axis tells us that this point is going to be on the unit circle as well. So go ahead and pause again and try to write the coordinates of that point before you push play again. Okay, so I'm sure you guessed correctly that this should be, notice the x value is the same and the y value is just going to be the opposite. So negative b, because y values are negative down here. And symmetry with respect to origin tells us that this point over here in the 3rd quadrant is going to be on the unit circle as well. Go ahead and pause the video and write the coordinates of that point and then push play. Okay, so as I'm sure you realize, this is the point negative A, negative B. So basically, there's a really nice rectangle to keep in mind, which is right there. Now, this rectangle, well, this, auto feature kind of made it look more like a square, but it's actually the one connecting all those points. So let me go ahead and put this point further here to make it look nicer. So basically, we're going to use this rectangle to find values of some of the points we're familiar with, some of the angle measures we're familiar with very easily. So do please at this point, pause, make sure you completely absorb this before you carry on. Okay, so next we will go ahead and use what we know about 30, 60, 90 and 45, 45, 90 triangles to try to at least fill out what we can on the unit circle in the first quadrant. So of course, for a 0 degree or 0 radian angle, the coordinates are simple. It's 1, 0. And also for a 90 degree or pi over 2 angle, coordinates are also simple. They're 0, 1. So now if we look at the 45, 45, 90 triangle, that'll help us come up with the values for pi over 4, which, if you recall, is the same as 45 degrees. So we can put that here just as a reminder. And for a 30 degree angle, if you recall, that's the same as pi over 6. 180 degrees divided by 6 equals 30. And also for a, okay, this is not cooperating here. Here we go. And for a 60 degree angle, these are approximate locations. Notice that's the same as pi over 3. So we know that on the unit circle, the x coordinate is going to be the cosine of the corresponding angle, and the y coordinate is going to be the sine of the corresponding angle. So if we look at pi over 6, which is the same as a 30 degree angle, and we go to our reference 30, 60, 90 triangle, we can see that the cosine of 30 would be square root of 3, which is the side adjacent, over 2. So we know that's going to be the x value for pi over 6. Now, as far as the y value, we know that's going to be the sine of 30 degrees, or pi over 6, which we can know from the reference triangle is opposite over hypotenuse, so 1 over 2. For pi over 4, which is 45 degrees, we can go to this triangle, and we know that the side adjacent to 45 is going to be 1, and the hypotenuse is square root of 2. So we have 1 over square root of 2, and notice the side opposite is also 1. So we are going to get 1 over square root of 2 again. For a 60 degree angle, we go back to our 30, 60, 90 triangle, and this time we're looking at the 60 degree angle. For the cosine, it's going to be adjacent, which is 1 over hypotenuse, which is 2. And for the sine, we're going to get opposite, which is square root of 3 over hypotenuse, which is 2. So we get that. Now we can calculate the sines and cosines of all the related angles in the other 3 quadrants based on that symmetry rectangle that we discussed in the previous part of this lecture. So for example, let's say we want to find the 6 trigonometric functions for 11 pi over 3. So what we're going to do, first of all, locate where 11 pi over 3 falls on the unit circle. Notice that 11 pi over 3 you can think of as 3 and 2/3 pi. So you can either plug in 180 degrees for pi, calculate it out, and see what degree measure that corresponds to, or you can just directly work with radians, which is what I recommend. So we know that starting here, we go half a circle, that's 1 pi, another half, that's 2 pi. So 3 pi, we're back here where pi was. And from here, we're going to keep going in the counterclockwise direction because it's positive, and we're going to go 2/3 more of a pi. So let's say 1/3 is about here, 2/3 will be about there. So we know that 11 pi over 3 falls here. So if we construct our rectangle, we realize that this is going to be a relative of, we don't really need all the sides, but we're just doing it for aesthetic reasons. And notice that this is going to be a relative of pi over 3. So all we need to do to get the coordinates for 11 pi over 3 is adjust the signs, that's SI, and S, for the values that correspond to pi over 3. So as we can see, the x value is going to be the same, so it remains positive 1/2. And the y value in this quadrant is negative, so that's going to be negative square root of 3 over 2. So now we can write all the 6 function values easily. So sine of 11 pi over 3, cosine of 11 pi over 3, and tangent of 11 pi over 3. So notice that sine is always the y value. So that's going to be negative square root of 3 over 2. The cosine is going to be the x value. So that's going to be 1/2. And for the tangent, all we have to do is divide the sine by the cosine. Or y over x. So we're going to get negative square root of 3 over 2 over 1/2. Then we can do the outer product over inner product trick to get negative 2 radical 3 over 2, and then simplify it to get simply negative radical 3. So there is the value of the tangent, and of course the other 3 values are simple, just take the reciprocal of those. So for cosecant of 11 pi over 3, we're going to take the reciprocal of the sine, which is going to be negative 2 over radical 3. And we usually like to present our answers in rationalized denominator form. So we're going to multiply top and bottom by square root of 3. And we end up with negative 2 square root of 3 over 3. So that's the cosecant. For the secant of 11 pi over 3, we're going to take the reciprocal of the cosine function, so that's going to be 2 over 1, or just simply 2. And for the cotangent of 11 pi over 3, we're going to take the reciprocal of the tangent function, so we're going to have negative 1 over square root of 3, and if we rationalize that by multiplying by square root of 3 over square root of 3, we end up with negative square root of 3 over 3. So that's how we can go ahead and find all the values for that particular angle using only the first quadrant values from the unit circle. So at this point, I would like you to go ahead and pause and try to do the same thing for 5 pi over 6. And then when you're finished, come back and hit play again. Okay, so you were asked to try to come up with the values for the angle corresponding to 5 pi over 6 radians. And if you notice that if you go start here and go all the way to a half circle, that's 6 pi over 6 or pi. So we need to go pi over 6 just shy of that right there. And if you notice, if we use one of the sides of that symmetry rectangle, we realize that the relative of 5 pi over 6, the reference angle would be pi over 6. And we know the values for that, square root of 3 over 2 and 1/2. So all we have to do to get the coordinates for 5 pi over 6 is adjust the signs. So because in this quadrant, which is the second quadrant, the x values are negatives, the square root of 3 over 2 is going to become negative square root of 3 over 2. And the y value remains positive and the same as that. So 1/2. So now we can easily write the values of the 6 trigonometric functions. So sine of 5 pi over 6, cosine of 5 pi over 6, tangent of 5 pi over 6. We'll start with those. We see that the cosine of sine of 5 pi over 6 is going to be the y value, so 1/2. The cosine of 5 pi over 6 is going to be the x value, which is negative square root of 3 over 2. And the tangent, we simply divide y by x, so, or the sine by the cosine. So 1/2 over negative square root of 3 over 2. We do outer product over inner product, and we get negative, always watch the sign, 2 square root of 3, I'm sorry, negative 2 over 2 square root of 3. 2 times 1 is 2, that goes on the top. 2 square root of 3 goes on the bottom. And the ones will cancel out, the 2's will cancel out, and we're going to go ahead and multiply by square root of 3 over square root of 3 to rationalize. So we end up with negative square root of 3 over 3. Now for the other 3 functions, we just take the reciprocal of these 3 values. So the cosecant of 5 pi over 6 will just be 2 over 1, which is 2. The secant of 5 pi over 6 is going to be negative 2 over radical 3, which is the reciprocal of the cosine. And if we rationalize it by multiplying top and bottom by square root of 3, we end up with negative 2 square root of 3 over 3. And lastly, for the cotangent of 5 pi over 6, we could take the reciprocal of this, or it's better actually to take the reciprocal of this one, which is negative 1 over square root of 3, because then we won't have to rationalize again. So we'll just go with negative square root of 3 over 1, which is just negative square root of 3. So you see that in this manner, given the value, given any angle which is related to any of these first quadrant angles through those symmetry rectangles which we discussed earlier, then to find the value of sine and cosine for that angle, we just basically see which one of these values in the first quadrant it's related to, and just adjust the signs to get the sine and cosine, after which we can get all the other values of the trigonometric functions. So make sure that you study this problem and fully understand these before you proceed. Okay, next we want to take a look at how would we find the sine or cosine of an angle if it doesn't happen to be one of the nice values in the first quadrant that we're familiar with, pi over 6, pi over 4, pi over 3, or one of the quadrantal angles, which are easy to find as well. So, for example, how would you find the cosine of, say, 1.5? So we know that corresponds, if you look on this unit circle here, and this is a great tool for learning. If you just go to Google and type trig and the unit circle Desmos into the search box, the first result that you get will bring you to this other site that I was showing you. So if you come in here, notice that this is just a unit circle that we have here, and if we go ahead and look at the A value over here, we can change it. So here we want the angle to be, say, 1.5, as we just mentioned. So you would just have to go ahead and change the 0, and you can ask it to label the ordered pair, so you can see for 0 radian angle, the cosine is 1, the sine is 0. We knew that. So if we just change that 0 to 1.8, actually 1.5 we were going to find, we can see that's what we would get for the value of the cosine. That's a good approximation, and that's what we would get for the value of sine. Now, this is actually a very handy tool because it gives you great intuition into what's going on. But it's of course not the most efficient way to go about this. And normally when we're dealing with an angle, which is not one of the basic ones that we're familiar with respect to the two special triangles, we go ahead and just use the Desmos as a calculator. So if we just go and type in, for instance, sine of 1.5, I haven't checked to see if Desmos is in radian mode, and it looks like it is. Okay, so notice the value that we got here is a much more accurate number than the value that you would get with a graphing tool such as the graphing aspect of Desmos anyway. So but it is a really nice tool to play with, because it gives you a great intuition into the unit circle and how the values of sine and cosine correspond to different locations on the unit circle. So for example, if we type in, instead of 1.5, say negative 2.5, see, we get our angle that's going to be here. So we start here, we go 1 radius, 2 radius, and then a half. So that would represent an angle whose measure is negative 2.5 radians. So the first value here would be the cosine of negative 2.5 radians, and the second value would be the sine of negative 2.5. And yeah, so that's simple enough to do. All right, but again, if we want a much more accurate answer, we just go either to Desmos or we can go to a TI, makes no difference, and we can just go ahead and type, sine of 1.5, and we can see the same answer, but with a fewer digits on than Desmos gave us. All right, so for those types of angles, we go ahead and use a calculator. Now, if you want the say cotangent or the tangent, you would need to actually use a reciprocal function. So for example, let's say that we want the cotangent of the same angle we were looking at, say 1.5. Okay, now if you look on a calculator, you're not going to find a cotangent button, so you're going to have to notice I didn't put a degree symbol, so that means we're dealing with radians. So you're just going to go 1 over the tangent of 1.5, and that's what you would enter into your calculator. So we're going to go 1 divided by tangent of, in Desmos you can just type TAN and it'll recognize it as tangent of 1.5, and that's where you find the answer for something like that. All right, so and then pay attention to the rounding instructions for the particular problem you're dealing with. So go ahead and see if you can find the secant of negative 2.5 using your calculator. So go ahead and get the answer and then hit pause right now, go find the answer, and then come back, we'll compare our answers. All right, so I'm hoping you're coming back from a pause. And of course, as you know, there is no secant button on the calculator either, so we're just going to go 1 over the cosine of negative 2.5. And that's what we will type into our calculator. So we just say 1 over the cosine of, whoops, too much, the cosine of negative 2.5. Again, make sure that when you do any of this, your calculator is in radian mode. All right, so go ahead and practice with a few of those, get comfortable with them, and then after you've mastered it, come on back to continue. Okay, so now we want to look at what happens if they give us either the sine or the cosine, such as in this case we have the cosine, in the next case we have the sine, in the third case we have the tangent, and what they ask us is for the angle itself. So if you notice, when we have that, if you recall, we need to invoke the inverse trigonometric functions. So if the cosine of theta is 0.9685, that means theta equals the inverse cosine of 0.9685. Now, we go ahead and calculate that. So if we go to our calculator, such as TI, we'll just go, Desmos has those as well. It's just TI lends itself a little bit more easily. But just so you know, in Desmos, you'd have to click the toolbar there and then go to functions, and there they are. Okay, so you can use that, or you can use the TI, whichever is available to you. So we're going to calculate the inverse. This is acting funny again. Okay, we want to calculate the inverse cosine of 0.9685. So we're going to bring up inverse cosine. Make sure you're in radian mode. 0.9685, and there we are. So then we give the answer to whatever level of accuracy they require. Looks like here they were thinking about rounding to 4 decimal places. So notice to 4 decimal places, 6 is the 4th place. So to the right of it is a 6. So we need to round up. So to 4 decimal places, this will be approximately 0.2517. So we just write approximately 0.2517. So there is the angle. Now, one thing we need to make sure is we need to pay attention to the quadrant requirements. Notice this is basically quadrant 1, but not exactly, because it's including the 2 quadrantal angles. So quadrant 1 plus the 2 quadrantal angles. So we notice that 0.2517 does in fact so if this is 1, you know that 1 is about right there, so 0.2587 is somewhere around there. Notice that does indeed satisfy the requirement that the angle that we want is between 0 and pi over 2. All right, so in this next one, we're going to find an angle in quadrant 3 whose sine is -1/2. I want you to go ahead and pause and see if you can get the answer on your own before you come back and push play. Okay, so I'm hoping that you recognize that as a sine value that you should be able to identify on the unit circle. Now, if you recall the original unit circle that we did, we had 1/2 in this location for the y value. So basically it was pi over 3. The angle was pi over 3 and pi over 6. I take that back. Sorry. Pi over 6. It was 30 degrees or pi over 6. And the values associated with it, if you recall, were square root of over 2, 3 over 2 for the x value, and 1/2 for the y value. But they want an angle in quadrant 3. That means in here. So that means basically between pi and 3 pi over 2. So that angle right there is not going to take care of business. So we need to go to the relative of that angle in the 3rd quadrant for the angle that we're looking for. So you can either just reason that, okay, that's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6. So you can just do it like that visually. Or if you're more algebraically oriented, you realize that just means take pi over 6 and add half a circle to it, which is pi. So we're going to take pi over 6 and add pi or pi over 1 to it, and you know that we need to combine those. So we get 6. This is already 6, so we need to multiply top and bottom of that by 6. So we get pi plus 6 pi, which is 7 pi over 6. The same result, of course. All right, so that's how you would handle a situation where they want an angle which is in a specific quadrant, and you know the exact value of, or you should know the exact value of. Okay, because if you give a calculator answer for something like that, neither my MATLAB is going to accept it, nor would I, because these angles that are fundamental ones from the 1st quadrant, you need to be able to know and recognize all those sine and cosine values. When it comes to tangent, there aren't that many that you're going to remember, but definitely one of them is when the tangent is 1. That should look familiar to you, and if you remember, it's the 45-degree angle whose tangent is 1, and the radian equivalent of that is pi over 4. So we know that Let's see if we can get this to recognize our circle. It's not doing so well this time. Here we go. Okay, so you know that if we look at pi over 4, we know the tangent of pi over 4 is 1 because the sine and cosine are the same. Now, I wrote those in rationalized form. Previously, we saw it as 1 over radical 2 comma 1 over radical 2. Both forms are acceptable. But this time, they want us to find an angle in almost the same description as the previous one, but a little technical difference. Because when you say quadrant 3, that's all these values from here to here, but not including pi or 3 pi over 2. When you put closed interval pi to 3 pi over 2, that means all of those angles including pi and 3 pi over 2. But we won't really need to worry about pi and 3 pi over 2 because we know where the angle is going to be. The angle is going to be right there, which is once again pi over 4 plus a pi, or you can just go that's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. And you know the coordinates are going to be negative square root of 2 over 2 and another negative square root of 2 over 2. So notice when you divide the sine by the cosine, you do indeed get 1. So theta equals, again, you could do it step by step like that visually, or you can just say it's going to be pi over 4 plus pi. And that's going to be 4 pi over 4 plus pi over 4, so 5 pi over 4 once again. All right, so that's how you would handle the situation if you're given the sine or cosine and you're asked for the angle. Go ahead and review that a little bit. Make sure you master it before you proceed. The best way to go on in learning mathematics is to allow the material to absorb. So take your time with these videos, let them absorb, and then proceed. This is the equivalent of in class situations where I do a problem, then I have you do one. That's the best way to learn these. Okay, next we want to take a look at this example from your PowerPoint, which looks kind of scary with that formula, but it's not. These are as far as word problems are concerned, some of the easier ones because all the pieces of the puzzle are given to you. You just need to plug in and evaluate. Where that formula comes from is an entirely different story, much more complex. And if you want to visually see the situation with this, it's also a significant geometric task. But basically the angle elevation theta of the sun in the sky at any latitude L. We already discussed the angle of elevation, so if you refer to your previous note, remember it's always measured from the horizontal, from the point of view toward the object. And at any latitude L, again we discussed that in the last lecture. Take a look at that video for a nice reminder of what the latitudinal angle looks like. And it's calculated using this formula: sine theta equals cosine d cosine L cosine, that's omega, lowercase Greek omega, plus sine d sine L. Now here theta equals 0 corresponds to sunrise, and theta equals pi over 2 corresponds to the sun being directly overhead. Omega is the number of radians that the earth has rotated through since noon, when omega is 0, and d is the declination of the sun, which varies between earth because the earth is tilted on its axis. Now here they're going to give you a scenario with Sacramento, California being at this latitude, 38.5 degrees, which of course you need to convert to radians, and they do so for you here. Find the angle of elevation theta of the sun at 3 p.m. on this date, February 29th, 2012, and we know that the angle of declination of the sun was approximately negative 0.1425 and omega approximately 0.7854. So this is just a matter of plugging in. So carefully substitute all those values in your calculator and you should get the result. So don't let the appearance of something scare you, but do be careful, because if you go back to the original problem, they wanted you to find the angle of elevation theta. But if you notice in this formula, look, it doesn't give you theta, does it? It gives you sine of theta. So the value that we found with this calculation was not theta, but the sine of theta. Now we're going to have to use the inverse sine function here to get the actual value for theta. But when we get that, remember, this is going to be in radians. So we still are going to have to convert that to degrees. So we're going to go ahead and multiply it by 180 over pi. That's where you get the approximately 27.3 degrees as the angle of elevation of the sun. All right, I know this has been a long section, so you've been good troopers. Hang in there, we're almost done. Now, there is a really nice geometric interpretation of the unit circle. Notice that if we construct this really interesting graph in the following way, this original triangle within the circle is clear enough and familiar enough to you. Now, if you extend that radius, which is the part of the terminal side of this central angle theta, and then it's enough so that you can drop a perpendicular from here and intersect it, and keep going and do a similar thing here. Drop a perpendicular to the y-axis at the point of intersection here and keep going until all three of those lines intersect. Then what you encounter is three triangles of interest. One is this original one, the next one is this triangle OVR, and also OSU. Now, notice that because these two lines are both perpendicular to the same line, that makes them parallel. And therefore, this angle here and this angle here, the TUV angle, are alternate interior angles. So therefore, their measures are going to be equal. That's why I wrote the theta here. This wasn't in the original PowerPoint. So it turns out that we can use this nice picture, this graph, to write the values of all 6 trigonometric functions as a side, or as one of the sides of one of those 3 triangles that we discussed. This smaller one, this medium sized one, and this larger one. And that's actually quite a simple task. Notice that we can get cosine and sine just from this triangle itself, OPQ. Notice that inside that triangle, a cosine of the angle theta is going to correspond to adjacent, which is OQ, over the hypotenuse. But remember, this is a unit circle, so the hypotenuse here is going to measure 1. So we get OQ for the cosine of theta. Now, if you also notice in the same triangle, sine of theta is going to be opposite, which is PQ, over hypotenuse, which is 1. So that's where we get PQ over here. Now, for tangent and secant, we can look at this second triangle. So I'm wondering if you have already noticed what's interesting about those three triangles that we have looked at. Think about it for a minute and you'll see they all have something in common. So go pause the video for a minute and go try to figure out if you can tell me what is it that all three of those triangles have in common. There's a certain quality. Okay, I'm hoping that you have looked at them long enough to realize that the quality that all three of these triangles, OPQ, OVR, and OSU, have in common is that each of them has a side whose length is 1, and that's what makes this very clever. Notice in triangle OPQ, the side OP is 1. In triangle OVR, it's the side OR which is 1. Both OP and OR are radii in the same unit circle. And in triangle OSU, notice it's the side OS, which is 1. And that's what allows us to find the lengths of these segments so nicely. So notice that in the triangle OVR, the tangent of theta is going to be side opposite, which is VR, over the side adjacent, which is OR. But as we know, OR is 1. That's why we just get VR for the tangent of theta. And in the same triangle, notice that secant of theta can be found, and secant, as you know, is hypotenuse over adjacent. So in OVR, the hypotenuse is OV. And the side adjacent to theta right here is OR, which is, once again, 1. So that's why we get OV over 1, which is OV. And finally, for the last two trig functions, cosecant and cotangent, we go to this large triangle here. And remember, this angle here, TUV, is exactly theta again, because of the fact that these are alternate interior angles. So if you look at the cosecant of this triangle, SUO, you get, for cosecant, as you know, is hypotenuse over adjacent. So in this triangle, in the large triangle, the hypotenuse is right there, which is what OU, or you can write UO, makes no difference, OU. And it's actually, when you write OU without the bar on top of it, you mean the length of the segment OU. So, and over the side opposite, so in this triangle, in the large triangle, what's the side opposite theta? Notice it's OS, which, as you know, is a radius of the unit circle, so it's 1. So that's where you get OU for the cosecant of theta. And for cotangent, which is adjacent over opposite, look, for this angle, what's the side adjacent? US or SU. That's the length, we mean, of the side, of course, over OS, which is the side opposite that angle theta. So we get US over 1, which is just US. So in this nice way, you can state the length of each of these segments that is, drawn in blue using one of the trigonometric functions. So the cosine is just going to be OQ. We've already established that previously. The sine is PQ. Tangent is VR. Secant is OV. Cosecant is OU. And cotangent is US. So now what we're going to do is we're going to take this triangle where they give you the fact that the measure of TVU, this angle here, be careful, not that angle which we know is the same as theta, but they're giving us this angle here. is 60, and they want us to find all the lengths of those sides we just talked about in the previous graphic using what we already know about a 60-degree angle. So notice that if this angle TVU is 60, there is an angle right opposite it. See right there? These are called vertical angles. This angle and this angle. They're equal in measure. So if this is 60, that means this is also 60, right? Which makes theta how much? Exactly 30. So basically, you're doing this same problem that we just looked at with this being a 30-degree angle. So rather than using the lengths of the sides, which we don't know, we're actually going to use what we know about a 30-degree angle and come up with those values that we need. So you know that, for example, the sine of, if you look at take a quick look at a 30-degree angle in the unit circle, that corresponds to pi over 6, right? Pi over 6 and 30 degrees correspond to the same location. And notice we already know the values. The cosine is square root of 3 over 2, and the sine is 1/2. You're going to want to get these down really solid so that you don't really have to think about them much, because we're going to use them a lot. All right, so the 30-degree angle is actually located there. So if you just write it there, that's more clear. All right, so we already know what the trig functions are for a 30-degree angle, because if you just go back to your 30, 60, 90, or just use these values, right? It may even be easier if we look at our 30, 60, 90 triangle. So let's say this is 30, this is 60, and that's 90. So for sine and cosine, we can just use those, but it's a little bit easier to come up with the other values if we look at the triangle. So we know that in this reference 30, 60, 90, the side opposite 30 is 1, the side opposite 60 is square root of 3, and the side opposite 90 is 2. So let's go ahead and write all the 6 trig functions. So we have sine of 30 degrees equals square 1/2. The cosine, remember, sine is the y value. The cosine of 30 degrees is going to be the x value, which is square root of 3 over 2. The tangent of 30 degrees, as you know, now let's go to this, it'll make it a little bit easier. Tangent, as you know, is opposite over adjacent. So 1 over square root of 3, and if we rationalize by multiplying by square root of 3, we end up with square root of 3 over 3. All right, so we also know that the cosecant of 30 is just going to be the reciprocal of that, so 2 over 1, which is 2. The secant of 30 degrees is going to be 2 over radical 3, the reciprocal of the cosine, which if we rationalize, we end up with 2 radical 3 over 3. And the cotangent of 30 degrees is going to be, it's easier to reciprocate that, because then we won't have to rationalize again. So square root of 3 over 1, which is just square root of 3. So now we know the length of each of those sides if we just look at, so let me make this smaller again. All right, so if we look at this graphic here, notice we had that the cosine of theta is OQ. So all we have to do is here, since we're dealing with a 30-degree angle, we know that's going to be the OQ that we were looking for. Now, if we want the sine, that's going to be PQ. For the tangent, that's going to be VR. Secant is going to be OV. The cosecant is going to be OU. And the cotangent is going to be US. So what we just did was, in this picture right here, the original one we were looking at, we just found the lengths of PQ, OQ, VR, OU, OV, and US, using what we already knew about the sine, cosine, tangent, cosecant, secant, and cotangent of 30 degrees. And that should bring us to the end of this lecture. So this was a long lecture. Please take your time to absorb it and then try your homework problems. So have a great day, and I'll see you for the next lecture.